This is section 11, related rates, example 2. Example 2. A spherical balloon is inflated at the rate of 10 meters cubed per minute. Find the rate at which the surface area of the balloon, that's supposed to say area, is increasing when the radius of the sphere is 3 meters. They tell us that S equals 4 pi r squared. We have a picture here. Now let's go through everything they give us. A spherical balloon is inflated at the rate of 10 meters cubed per minute. So that's the rate at which the spherical balloon is being inflated. Now, surface area is not the rate at which something is being inflated. Okay, that's the change in surface area. So they've actually given us the change in volume of the sphere, which means that we're going to have to use that somehow, right? That is a thing that they gave us, even though it's not written anywhere in here that we're going to be dealing with volume. But we know that if something's inflating at a cubic rate, then that's going to be volume. So dV dt is 10 meters cubed per minute. All right, it says find the rate at which the surface area of the balloon is increasing. So we need to find ds dt. That's what we don't know. When the radius is 3. Okay. Now, if I'm dealing with volume, I probably need to write down somewhere the volume formula, and if I'm finding surface area, I probably need to write down somewhere the surface area formula. So let's go ahead and do that. So V, the volume of a sphere is 4/3 pi r cubed. That's the formula. And the surface area of a sphere is what's there, 4 pi r squared. Okay, so I wrote down the formulas. Now we're going to differentiate. We're going to differentiate both of them. And the reason we're going to differentiate both of them is because it gives me dV dt, so I know I need to get dV dt. We're solving for ds dt, so I need to get ds dt, and the only way to find that rate of change is to take the derivative. So dV dt equals 4 pi r squared dr dt, and ds dt is 8 pi r dr dt. Now, notice there's something in both of these equations that we don't have, and that is dr dt. The wonderful thing, the really cool thing, is that we actually don't even need to know what that is. We need to solve for it in one equation so we can plug it into the other one. And it's going to be beneficial for us to solve for the one where we know everything. So if we look at this, at the green equation, dV dt, we know that. We know r. We don't know dr dt. Okay, that's one unknown that we need to figure out. In the purple equation, we don't know ds dt and we don't know dr dt. That's two unknowns. So if we solve for dr dt in the purple equation, it's not as beneficial. We need to solve for dr dt in the green equation. So let's go ahead and do that. So we're going to divide by 4 pi r squared, which means that dr dt is equal to dV dt divided by 4 pi r squared. Now we're going to take that and plug it into the purple equation where we have dr dt, which means that ds dt, which is what we're solving for, is 8 pi r times dV dt over 4 pi r squared. Now, just using my vast knowledge of algebra, right, I can cancel some stuff out. I know that the 4 and the 8 will cancel to make a 2. The pi's cancel. The r just becomes r on the bottom. And so I really just have 2 dV dt over r. which is much simpler to look at. And once I do that, once I do the plugging in, I'm going to be done with this problem. So, ds dt is equal to 2 times dv dt was 10 cubic meters per minute, and r was 3 meters. All right, so that's it. It's 2 times 10 is 20 over 3. And then 1 meter cancels with that, so it's meters squared per minute. And surface area is in meters squared. And then it's a rate, so it's per minute. And that makes sense.